Hey there, welcome to AP Statistics Quideo number 4. Today, let's start with the basic question. So the basic question talks about a Gallup poll that asks the probability sample of 1,785 adults whether or not they attended church or synagogue. Now, suppose 40% of the adult population did attend. We would like to know the percentage that an SRS of this size, 1785, would come within plus or minus 3 percentage points of the true population proportion. Now, let's start with question A. So question A asks, if p hat is the proportion of the sample who did attend church, what is the mean sampling distribution of p hat, and what is the standard deviation? So we're going to be looking at two formulas here. First was not really a formula, but more a fact that whenever you have a sampling distribution p hat, the mean of that sampling distribution is always going to be equal to that value. So in this case, 40% is given. So we use 0.4 as our mean, which is also our p hat. So that's going to be our mean sampling distribution, 0.4. Now, the standard deviation of the sampling distribution p hat does have a formula. So this is going to be the square root of p times 1 minus p over n, or in other words, pq over n if you like that better. So when you plug in your values, p is equal to 0.4, 1 minus p, or q, is equal to 0.6, and your n is your population, or I'm sorry, your sample size, which in this case is 1,785. So when you plug that in, your standard deviation of your population, or your sample proportion p hat, is equal to 0.0116. Next, let's look at parts B and C. So part B talks about why you can use the formula for the standard deviation of p hat in this setting, and part C checks that you can use the normal approximation for the distribution of p hat, so using your rule of thumb number 2. So let's look at those. So the population must be 10 times the sample size to use this formula for the standard deviation. So in this case, your population must be at least 10 times your sample of 1,785, so your population has to be at least 17,850 adults. Now, if we think about it, are there at least 17,850 adults in the United States that they could theoretically take the poll or a poll of? Yes, of course, the population is well above 17,850 adults. So we can check that off. That satisfies rule of thumb 1 and allows us to use this formula for the standard deviation. So then let's look at question C. Question C asks if we are able to use the normal approximation, and it talks about rule of thumb number 2 from the textbook. So rule of thumb number 2 basically says that NP is going to be greater than or equal to 10, and NQ is going to be greater than or equal to 10. So that's saying that the number of people in the sample, N, times the probability, P, or the proportion rather, not probability, is going to be equal to 10, and then N times 1 minus P, or Q, is also going to be equal to or greater than 10. So in this case, you plug in your values, 1,785 times 0.4, which is equal to 714, much more than 10. And then same thing for the NQ test, 1,785 times 1 minus 0.4, or 0.6, is equal to 1,071, also much greater than 10. So that solves your problem. You can use the fact that it's normal to approximate the mean and the standard deviation, and just kind of view it as a normally distributed proportion. Lastly, we're going to be looking at question D. So question D is asking what's the probability of using a simple random sample of 1,785 adults to find a p hat value between 0.37 and 0.43, so around 3 percentage points of the given mean of 0.4. So let's jump into this. First, we're going to be looking at our assumptions, many of which we solved for already. So first, the SRS is given in the problem that we found a simple random sample of these 1,785 adults. That's good. Then we're going to look at the independence. Now, if you look at part B, we prove independence by saying that the population is at least 10 times the size of the sample. So because that checks out, we can use not only this, we can also use that as satisfying our assumption of independence. Last, we're going to use our normality assumption, which basically, in this case, because we're talking about proportion, says NP is greater than or equal to 10, NQ is greater than or equal to 10. So part B and C solve our second two assumptions. SRS is given. This basically allows us to proceed forward and really without having any restrictions on what we can do, what we can assume, what we can calculate. So it's asking us to find the probability that the p hat value is going to be in between 0.37 and 0.43. So first, I like to find the low z value. So in this case, your z is going to be equal to p hat minus p over the standard deviation of p hat. So our p hat value in this case is the low end of probability, or the low end proportion rather, that they're given, so 0.37 minus 0.4, which is the understood population proportion, over 0.0116, which we solved for up there. And then when you plug that in, you get a z-value of negative 2.586. Now, you're going to go in your textbook on table A. I don't have table A with me right now, but you go through table A, you find that your probability of getting a z-value less than or equal to negative 2.586 is 0.0048. So pretty low, but not as low as possible. It's not zero. It's still possible. Then you're going to do the same thing, but with your high-end z. So in this case, your high-end sample proportion, is going to be 0.43 because that's the high end of the 6-point interval that you're testing, 3 on each side. Your 0.4 is still your p-value, your population proportion, and your standard deviation is still the same, 0.0116. So you look at it and you actually get the same exact number, but positive instead of negative. Then you solve using the same way with table A, which I don't have right now, but you're going to have to trust me on it or go check for yourself. And you get a probability of 0.9952. So you've calculated the probability of finding z-values below the high end of our range and the low end of our range. So the probability of x, your actual proportion, being between 0.37 and 0.43 is equal to the probability that your z-value is going to be equal to your two z-values you found here, negative 2.586 and positive 2.586. In order to solve that, you're going to take the probability that's less than the greater one and subtract the probability that's less than the lesser one from the greater one. So I know that was a lot of words and it's confusing, but you're going to go back up to this value, the larger one, and subtract the smaller one from the larger one. So 0.9952 minus 0.0048 equals 0.9904. That's a pretty high percentage. That's your probability that it's going to be in between 0.37 and 0.43. That's probability that's going to be your range of proportions given you have a repeated simple random sample. So because the probability that your p-hat is going to be within 3% of the true population proportion, which is going to be 0.4, is so high, it's 0.9904, over 99%, we can safely assume with over 99% certainty that in repeated trials with a simple random sample of 1,785, that the resulting p-hat is going to be within 3%. Because 99% certainty is almost perfectly certain that you can say that whatever it is going to happen. And the reason that's the case is because you have a low-end p-value that is so many standard deviations below. It's 2.586 standard deviations below, and the high end, which is 2.586 standard deviations above, that encompasses so much of the normal curve, the normal distribution of this model, that it allows us to make a pretty strong assumption, pretty firm assumption that whatever we're saying in this case, the plus or minus 3 percentage points, is going to be true. So that is the end of the basic question. Alright, next we're going to look at the advanced question. So the advanced question looks at researchers who are interested in comparing two methods of estimating tire wear. The first method used gives the amount of weight lost by each tire, and the second one calculates or measures the amount of groove wear in each tire. So a random sample of 16 tires was taken to try to calculate the difference between these two, and it's given here in this column in thousands of miles for each tire. So the first part of this question, part A, asks us to construct and interpret a 95% confidence interval for the mean difference mu in the estimates from these two methods of in the population of tires. So let's start. Whenever you're given a question that asks us to make and interpret a confidence interval, whether it's 95%, 90%, 99%, whatever, the first thing you want to do is go directly to PANTS. So PANTS standing for parameter, assumptions, name the test the test, and make a concluding statement. So first, let's look at the p-value, the parameter. So the parameter in this case is the mean difference between the weight lost by the tire and the wear in its grooves. Or simply put, it's the difference between the two measures of tire wear, also in thousands of miles. So you want to state the parameter just so you make sure you're proceeding and you're going forward and knowing exactly what you're calculating and what you can write in your concluding sentence for S. But we're not there yet. So let's go into A. A in this case, or in all cases, is the assumptions you're making. So your first assumption is going to be that it's a simple random sample. It gives you you don't really have to make this assumption, it gives you the fact that it's a simple random sample of 16 tires, so that's good, you can check that off. Next, you're going to assume independence. So a lot of times what you see when you see assuming independence is that your population size is going to be 10 times or greater than 10 times of your sample size. And we can assume that there's 160 or more tires in the whole population, which is a fair assumption because there's thousands and thousands and thousands of tires. So that's easily assumed. Next, we're going to look at normality. Now, we're talking about population means, sample means, so we will immediately think, okay, central limit theorem. However, our sample size is only 16. So that obviously does not support the idea of central limit theorem, which requires at least a sample of 30. So what I did next instead was I went and graphed all the values on the page you saw before and put them in a histogram. Now the histogram tells us one thing really. It tells us the shape, it tells us the distribution of the sample data. So in this case, you look at it, it's not very skewed one way or another. It seems not necessarily perfectly normal, but because there's no noticeable skew, we can assume normality for our purposes. And you can assume normality for both the sample and the population so that you can accurately calculate your confidence interval. So next, you're going to be talking about naming the test. Once you get your assumptions done, you can move forward. But I would say one thing, you want to proceed with caution because you don't necessarily know for 100% fact that it's going to be normal because we can't prove the central limit theorem. Okay, back to naming the test. We're going to be using a one sample t interval. We're using a one sample because we're only given one sample of data, just the differences. We're not actually worrying specifically about the weight and grooves individually because they give us the difference column. We're using a t interval because we're given sample data and sample standard deviation rather than population standard deviation. So we're going to take your t values, we're going to take your standard deviation, we're going to take your mean, we're going to take your sample size, and we're going to go ahead and make a confidence interval out of that. So we look at the t star component of it. So here's your equation for your one sample t interval. But let's look at the first part, t star. Now what does that mean? That's sort of like your z star, but instead of using table A, we're going to look at table C. Now you have a sample size of 16 people. So in order to find your degrees of freedom, your df value, you do 16 minus 1, or 15 right there. Now you also have a 95% confidence interval, and because it's a two-sided interval, each side is going to have 0.025 in area on either end of the tail. So you go up to 0.025, and you basically connect your degrees of freedom, 15, to your 0.025 value, and you get this 2.131 t star. So that's the value we're going to be using for t star going forward. So once you have that picked out, you can go, see, that's why I said there's the explanation of that. You can go ahead and calculate the mean and standard deviation. So I took the liberty of putting all the values in here, and all you're gonna have to do is go to stat, calc, one variable statistics, and go to calculate, and there's your mean and standard deviation, and I copied them down there so you can see them a little better. And as I said before, there's a sample of 16 randomly selected tires. Okay, so let's go back to the formula here. Your formula for your margin of error is going to be mean plus or minus t star times the standard deviation of the sample over the square root of your sample size, n. Let's plug in all your numbers. You get 4.5563 plus or minus 3.2255 divided by the square root of 16. This is also going to be equal to 4.5563 plus or minus 1.7184. Now in order to get your confidence interval in interval notation like this, you're going to subtract 1.7184 and add 1.7184 from your mean 4.5563, and that's your interval right there. So that's how you test the test. It seems redundant, but that's what you got to do. All right, lastly, we're going to go to the S part, your statement, your conclusion statement. Now what you're going to do here is you're basically going to tie your parameter to your findings to your assertion and your conclusion about how confident you can be in the given interval. So our statement in this case is that we are 95% confident that the true population mean difference between the two measures of tire wear in the weight lost by the tire and the grooves, or the wear in the grooves, measured in thousands of miles, is between 2.8379 thousand miles and 6.2747 thousand miles. So this basically tells us that in repeated random samples of this size of 16, we are going to get a mean difference of between 2.8379 thousand miles and 6.2747 thousand miles. So we can safely say with 95% confidence that in repeated samples it's going to be somewhere in that range of values. Okay, so next we're going to see, does your interval in part A give convincing evidence of a difference in the two methods of estimating tire wear? Justify your answer. So we're going to look back at our interval we found in part A, which is right here. And we're going to say, okay, well, this basically tells us that 95% of the time, if you repeat your samples over and over and over again of this size, you're going to get a mean difference between these two values, 95% of the time. So you're fairly confident, 95% confident, that there's going to be at least a difference of 2.8379 between the two methods of trials. So because there is a noticeable difference, there's that 2.8379 difference, in 95% of trials, at the very least, there's only going to be maybe 0.025% of trials, 2.5% of trials that are going to be any less than that. And even then, those trials might still be some difference. They're still going to be greater than 0. So had we got in a range that included 0 or included values of negative, anything like that, I mean, we could say that there isn't going to be definitive evidence that there is a difference between the two methods. But because our 95% confidence interval encompasses all positive values and doesn't include 0, it doesn't include no difference, we can safely assume with this 95% confidence that there is going to be some difference in between the two different methods of testing tires. Lastly, let's look at the AP question. So it talks about golf balls needing to pass a set of 5 standards in order to be used in professional tournaments. So one of these is distance, and it's calculated by being hit by this thing called iron Byron at a 10-degree launch angle with a backspin of 40 revolutions per second and a ball velocity of 235 feet per second. And the distance the ball may travel must not exceed 291.2 yards. So that's a lot of information, and a lot of it's in fact, it's irrelevant. You really just need the 291.2 yards because that's your maximum distance. We're not talking about physics or angles or anything like that. It's really just the distance traveled. So you can kind of disregard everything else but the 291.2. So a particular manufacturer has determined that the distances traveled with the balls produces a normally distributed curve with a standard deviation of 2.8 yards. So you have all this information. Really, what you're getting out of this is they're hit and they can't go over 291.2 yards, and they have a standard deviation of 2.8 yards. Okay, so they have now developed a new process where they can determine the mean of the distance that it travels. If it's going to go over, it's going to go under, but that's going to be the mean. So if the manufacturer sets the mean distance traveled to be equal to 288 yards, what is the probability that the ball is going to be randomly selected for testing will travel too far? So that's part A. Let's look at how we're going to solve part A. So we're given, as I said, the mean is 288 yards that they put in this machine, and the standard deviation is going to still be 2.8 yards. And we're also given that it's normally distributed. So you can say normal n 288, 2.8. That's like your shorthand notation to say it's a normal distribution with that mean and that standard deviation. So in order to find the probability that it's going to be lower than the 291.2 yards, you're going to look at finding a z value. So in this case, your z formula is x minus mu over sigma, or your given value minus the mean over the standard deviation. So you're going to plug in your values, 291.2, because that's your given value that you cannot exceed, minus 288, your mean, over 2.8, your standard deviation, and you get a z value of 1.1428. So the probability that x is going to be less than 291.2, the ball distance is going to be less than the max it can be, is also equal to the probability the z in your table is going to be less than 1.1428. Now, I don't have table A out right now, but you can go into your book and get table A is equal to 0.8729. So you're going to use the same thing where you're going to find what 1.1428 is in your book, and it's going to be 0.8729. So that's the probability that the ball is going to travel less than 291.2 yards. However, the question asks, what's the probability that if the mean is set at 288 yards, that the ball is going to travel greater than 291.2 yards? So in order to do that, all you have to do is find the complement of that probability, which is 1 minus 0.8729, which gives you 0.1271. So the probability that if you set the machine to have a mean of 288 yards, the probability that's going to be greater than 291.2, greater than the max it can exceed to be toward legal, is going to be 0.1271 or 12.71%. Alright, so part B says, assume the mean distance traveled is 288 yards and the 5 balls are independently tested. What is the probability that at least one of the 5 balls will exceed the maximum distance of 291.2 yards? So let's look at this. The probability of A that we found in part A of any ball exceeding the 291.2 yards is 0.1271. And we found that because we used the normal distribution that we're given to accurately find a z-score and then apply the z-score table A and get 0.1271. So that's your probability that if you just fire a ball at any given time, that it's going to go over 291.2 yards. Now, we're going to look at the complement of the probability of A, which is the probability that any ball will not exceed 291.2 yards, which is 0.8729. So then let's transfer to probability of B, which I'm calling it, you can call it whatever you want, but for simplicity, let's call it probability B, which is the probability that all 5 balls stay under 291.2 yards. So all you have to do that is put the probability that any one ball stays under and put that to the 5th power, and you get 0.5068. So that's a probability that you shoot 5 balls off and that all of them stay under the 291.2 yards. So not too bad, it's about a 50-50. So lastly, probability C, which is what I'm calling it, not necessarily what you have to call it, is the probability that at least one ball goes over 291.2 yards. So that's what the question's asking you. And in order to find the probability that at least one of something happens, you do the probability of, or the complement of the probability that all of them don't do that. Because whatever is the remaining probability is the probability that any 1, 2, 3, 4, or even 5 in any type of combination go over 291.2 yards. So the probability that at least one ball goes over 291.2 yards is going to be the complement of probability B, which is 1 minus 0.5068, which is equal to 0.4932. So the probability that at least one ball, if fired off at a mean of 288, goes over 291.2 yards is 0.4932, or 49.32%. Lastly, let's look at part C. So part C says if the manufacturer wants to be 99% confident that randomly selected ball will not exceed the maximum distance of 291.2 yards, what is the largest mean that can be used in the manufacturing process? So what this question is asking is saying, what is the mean that we can use so that 99% of the time the ball is going to shoot, and only 1% of the time it's ever going to go over the maximum distance of 291.2. So for this, I went down and got my table A, and we're going to look at it like this. So when you say something is 99% confident, you're going to look at the value in the middle of the field that has its closest to 0.99 or 99%. So right here you see that it's 0.9901, and that gets you to 2.33, right? So 2.33 is your Z value. That basically says the probability of getting a Z under 2.33 or at 2.33 is going to be 99%. So that's the value you use for Z here. And then all you have to do is use your Z equation that we used above. Z is equal to X minus mean over standard deviation, and then manipulate a little bit. So Z times standard deviation is going to be equal to X minus the mean. And then you get that and go there. So negative Z times standard deviation plus X is equal to the mean. So that's the mean that you're going to find. You'd plug into the machine, and 99% of the time, the ball is going to be perfect. It's going to be less than 291.2 yards. So then at that point, all you have to do is plug in your values. 2.33 would be negative because that's how we solved it, times 2.8 plus 291.2, and that'll get you a mean of 284.676 yards. So to answer the question, in order to put a mean in that 99% of the time the ball is not going to exceed the maximum limit of 291.2 yards, you use a mean of 284.676 yards to satisfy your issue. So that's the end of the AP question, the end of AP Statistics Quideo number 4.